In this lecture, we're going to go over heat transfer and work in internally reversible steady flow processes. This is going to bring us to an end of chapter 6 in our course. So for a control volume at steady state, in which the flow is both isothermal and internally reversible, our energy rate balance becomes 0 is equal to our heat transfer plus our mass flow rate times our change in entropy, because there's no entropy production since it's internally reversible. So our heat transfer per unit mass is our temperature times our change in specific entropy. As temperature is going to vary as the gas or liquid flows, we're going to get that it's actually equal to the integral of TdS. If we look at work, the work per unit mass passing through the control volume can be found using our energy rate balance. So our work is equal to our heat transfer plus our change in enthalpy plus our change in kinetic plus our change in potential. If we only restrict ourselves to internally reversible processes, we can say that our work is equal to the integral from 1 to 2 of TdS plus our change in enthalpy plus our change in kinetic plus our change in potential. Since internal irreversibilities are absent, a massive unit traverses a sequence of equilibrium states as it passes from the inlet to the exit. Entropy, enthalpy, and pressure changes are reduced, so we can use our TdS equation, which tells us that the integral from 1 to 2 of TdS is equal to H2 minus H1 minus the integral of VdP. Which, if we use that into the equation we just developed for work, we get our work for an internally reversible process is equal minus the integral of VdP plus our change in kinetic plus our change in potential. So we're going to see how this applies to polytropic processes. If we use our polytropic relationship, we know that our work is equal to minus the integral from 1 to 2 of VdP, which equals minus a constant to the 1 over n times the integral from 1 to 2 of dP, or p to the 1 minus n, which equals minus n for n minus 1, p2 v2 minus p1 v1, or n cannot equal 1. If n is equal to 1, we get that our work is going to be equal to the integral from 1 to 2 For an ideal gas, our equations are going to reduce even further. We're going to get that our work is equal to minus nR over n minus 1 and T2 minus T1. For a polytropic process of an ideal gas, we can use our polytropic process relationships. Thus, we get that our work is equal to minus R N R T1 for N minus 1 times P2 over P1 to the N minus 1 over N minus 1. And if N is equal to 1, we get our work is equal to minus RT times the natural log of P2 minus P1. So this is for internally reversible polytropic processes. So if we look at an example, we have an air compressor operating at steady state with air entering at 1 bar and a temperature of 20 degrees Celsius and exiting at 5 bar. We want to determine the work and heat transfer per unit mass as the air undergoes a polytropic process with N equals 1.3. We're going to neglect changes in kinetic and potential energy between the inlet and outlet. So to determine both the work and the heat transfer, we need T2. We're going to get T2 because it's a polytropic process. We have T2 equals T1 which is 293 times 5 over 1 to the 1.3 minus 1 over 1.3, which tells us that T2 is 425 Kelvin. So our work is equal to minus NR over N minus 1. T2 minus T1 is minus 1.3. Our work is minus 164.2 kilojoules per kilogram. Our heat transfer, we're going to do our energy balance. Our heat transfer is our work plus our change in enthalpy, which is equal to minus 164.2 and these are from table A22. We get that our heat transfer per unit mass is equal to minus 31 kilojoules per kilogram. Our last example, we have an electrically driven pump operating at steady state and draws water from a pond at a pressure of 1 bar and a rate of 50 kilograms per second, and delivers water at a pressure of 4 bar. There are no significant heat transfers to the surrounding or changes in kinetic and potential energy. The isentropic pump efficiency is 75%. Evaluating electricity at 8.5 cents per kilowatt hour, we want to estimate the operation cost of the pump. So the power for our pump in terms of magnitude is going to be our internally reversible work over our pump efficiency, where our internally reversible work is our specific volume times our change in pressures, which happens to be P2 minus P1 over our density using the definition of specific volume. So the work for our pump is equal to our mass flow rate times our change in pressure divided by our density times our pump efficiency, which is 50 kilograms per second, times 4 minus 1 bar over 10 to the 3 kilograms per meters cubed times 0.75 times 100 kilopascals per bar, and we get an answer of 20 kilowatts. So our cost is our power times time times cost, which is 20 kilowatts times 1 hour times 0.85 dollars per kilowatt hour, which comes to $1.70. So this lecture gave us a new way to calculate internally reversible work. And that is it for the course.